Okay, the first thing that I want you to see is that a straight angle is 180 degrees. So, I'm going to start with my protractor, and I'm going to draw a ray. Here is a ray. Then I'm going to line this up, and I'm going to measure around 180 degrees, which is over here. Then I'm going to draw another ray. Lo and behold, a straight angle, well, that's not lined up very well, is it? That's funny. A straight angle is 180 degrees, and you can see that on this protractor too. Okay, if you start here and you count all the way around, it's 180. If you start on this outside scale all the way around, it's 180. 180 is a straight line. So, one of the things that we said is that the sum of all measures of a triangle, the angles of a triangle, is equal to 180 degrees. So, let's prove it. Here is an equilateral triangle. Here is an acute equilateral triangle, Here is a right triangle, and here is an obtuse triangle. These three angles should add up to 180 degrees for a straight line. These three should add up to 180 degrees. These three should add up to 180 degrees. And it doesn't matter what these triangles are. They're not any special triangles. You can see these were brought to you courtesy of C&E Paving. Thank you, C&E Paving. I just cut them out of a piece of paper. It doesn't matter. A triangle, all angles of a triangle always add up to 180. So let's prove it. Let's take this acute equilateral triangle first. Now I marked the angles on here just so once I cut my paper up, it'll be easier to line these things up. This is cut up into three pieces. If I take these pieces and I put the angles together along this line, like this, look at that. They form a 180 degree straight angle because the sum of the angles of a triangle always add up to 180. Now let's try this one, my right triangle. So it worked for an acute, should work for a right. This one's really small. I don't know what I was thinking making one this tiny. Okay, take this, we'll line it up right there. Now we'll take another angle, put it in here, and then we have one more angle to do, and it is a 90, and look at that. Voila! 180 degrees. Beautiful. I love it when things work. Now we'll take this obtuse, cut that off. Cut that off. Let's line up these. There's my angle. There's my other angle. And the last one, will it work? Of course it works, because in math, the sum of the angles of a triangle always equals 180 degrees or a straight line. Thank you very much. So now that we know that triangles all have a total angular measure of 180 degrees, we're going to use that to find the measure, total angular measure of other polygons. Let's start first with a quadrilateral. Okay. Not the best, I understand. Again, what we're going to do is use what we know about triangles to find the total angular measure of this shape. What you want to do is you want to pick a vertex, or in other words a corner, and from that corner you want to draw a diagonal inside the shape. Diagonal goes from one vertex to another vertex, but it cannot trace over the sides. So here I can only draw one. When I do that, I split this rectangle, this polygon, this quadrilateral, into two triangles. This one has a measure of 180 degrees. This one has a measure of 180 degrees. So you take the number of triangles in the shape times total angular measure for a triangle, and you find out that a quadrilateral has a total angular measure of 360 degrees. And it doesn't matter what type of quadrilateral it is. So here, let's try this one. What would you call this one? Maybe you remember, trapezoid. Pick one vertex, go across, two triangles. Still has a total measure 360 degrees. Let me try a pentagon. Oh boy, this is going to be a bad pentagon. Sorry. There. All right, there's my pentagon. 5 sides, 1, 2, 3, 4, 5. Penta stands for 5. And gon actually comes from the Greek origin gonia, which means angles. So 5 angles, 5 sides, 5 angles, doesn't matter. All right, pick again a vertex. Do not trace over a side. but draw in the diagonals. This time you're split into 3 triangles, each with a measure of 180 degrees, 3 times 180, 540 degrees for a pentagon. Now, if you notice, here there are 5 sides or 5 angles, and the number of triangles is 3. Here, there's 4, and the number is 2. The number of triangles that would be inside a shape is always 2 less than the number of sides. So here we had 4 sides minus 2 gives me 2 triangles. 5 sides minus 2 gives me 3. So, for example, let me try, the only other shape I think I could draw is probably an octagon, because I see them all the time when I drive. Where are they? Stop signs! Okay, that's not a good one. Okay, anyway. There are 1, 2, 3, 4, 5, 6, 7, 8 sides. So we would expect that the number of triangles is going to be 2 less. We would have 6 times 180 is equal to 1080 degrees for an octagon. Let's check though, just to make sure. Here, 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 and down here. And what do I have? I have 1, 2, 3, 4, 5, 6. The number of sides is 8 minus 2 gives me the number of triangles that would be inside. Pretty cool, huh? So that way you don't actually have to draw everything. If I said, what is the total angular measure of a 22-sided figure? You would just take 20 times 180. Pretty cool. Okay, we're going to talk about area next. Area is the amount of two-dimensional space an object takes up. On my work table right now, if I put this piece of paper down, this piece of paper is taking up a certain amount of space, like a rug would on the floor or paint would on the wall. So it's two-dimensional, it's not three-dimensional, it doesn't come towards you. I have a rectangle here, or parallelogram. And when you were in elementary school, you learned that if you were finding the area, the amount of space an object took up, what you would do is you would take a ruler and you would measure. And you would say, all right, well, this is 4 inches, and this side is 3 inches. And then your teacher would have you split this thing up, or it would be split up for you, into boxes. So you can find the number of square inches in this object. Let me do this real quick. And this was just to prove a point, because it's obviously something you wouldn't want to do all the time. It's very tedious. And then you would say, all right, well, this object has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 square inches, or 12 inches squared. And then later on you learn that, well, there's a shortcut to this. What you could do is you could do length times the width. So 4 times 3 is 12. Inches times inches, because there's 2 of them, gives you inches squared. And that was very helpful. Then you went on to other parallelograms, and it was base times height. And squares, you may have been told that are side times side. But what I'm telling you is it's a lot easier if you just say, think of all parallelograms as being a base and a height. And you're doing base times height for the parallelogram to find out the area. The height is always just a perpendicular distance. So here's perpendicular, meaning 90 degrees, distance from the base to the other side. So you could, instead of saying width, just say height. Now, let's show you, here's another rectangle. If I wanted to find the area of this rectangle, I would take the base times the height, and the height again is the perpendicular distance from the base to the other side. So I would just take, on my table, area is equal to the base times the height. And we know that already because we split it up on the drawing before. If I were to take this object and cut it, I'm going to cut this rectangle. What I did is I created 2 shapes, but the area is still the same. If I put it together, I didn't change it. This piece plus this piece is still the same area. So that means if I change the order of them, it still has the same area. If I take this and put it over here, it still has the same area. because it's still a parallelogram. This side's parallel to this side's parallel to this. So you take the base, this is just this other part of the base, now it's over here, times the height, which is the perpendicular distance from the base to the other side. We're actually going to use this information to discover the area or area formulas for triangles, trapezoids, and even circles. Okay, that is all. To find the area of a triangle, I think it's best to start with a parallelogram. If you remember, the area of a parallelogram is the base times the height, where the height is the perpendicular distance from the base to the other side. Triangles all can be derived from parallelograms. If this parallelogram is base times height, and you took it and you cut it in half exactly, you end up with two triangles. This one is half of the base times height. This one is the other half of the base times height. Just to show that these are exactly the same, I'll put them on top of each other. You can see this is the same size. It's exactly half of the original parallelogram. So the area of a triangle is equal to 1/2 of the base times the height. That is all. Pretty simple, right? Alright, now we're going to find the area of a trapezoid. This is a trapezoid. And we're going to do that using what we know from a parallelogram. From parallelogram, we learned that you have a base and you have a height. And the height is the perpendicular distance from the base to the other side. Now, for a parallelogram, you would do base times height. However, this is not a parallelogram. It's not a parallelogram because it only has one pair of parallel sides. Quit rolling. These sides are not parallel. The easiest way to do this, though, to find the area of this shape, using what we know from a parallelogram, is to have two trapezoids. So if I take this, I just so happen to have two identical trapezoids. If I were to take this one and turn it around and put it with this one, you see, what do I have? It's not lined up very well, but I have a parallelogram. This side's parallel to this one. This side's parallel to this one. For a parallelogram, it is base times height. So here I have another base. This B represents just this one. This B represents this one. So what I'm going to do is I'm going to say, well, I'll call this one B1. I'll call this one B2. Then the area of this parallelogram is going to be equal to the two bases. I have to add them together. Base 1 plus base 2 times the height. And then you see, here's base 1, here's base 2. If I add them together, it's the total base of the parallelogram times the height. The problem is, this is for two trapezoids. I want to know just one of them. Well, since they're identical, I could take this whole thing and divide by 2, which is the same thing as multiplying by a half, by the way. And then I would know how much the area of just this one is. That leaves the only question of, all right, well, what is this other base 2 then in the formula on this shape? If you turn this back around, you'll see that base 2 is the top. When you're identifying the bases in a trapezoid, it's always the sides that are parallel to each other are the bases. And then the height is the perpendicular distance. So for one trapezoid, the area is that add the bases, multiply by the height, divide by 2. Okay, I want to talk to you guys about pi, and what is it exactly? Because anytime you talk about circles, you're always dealing with pi. So the easiest thing to do is for me to draw a circle first. So I'm going to use centimeters here. I have my compass, and I'm going to set it to a radius, which is half the distance of the circle, to 4 centimeters. And then what I'm going to do is draw a 4 centimeter circle. Oops, I touched it accidentally. Okay, so here is the center of my circle. I know because I had left a little point there. And I know that the radius, the distance to the outside, r, is equal to 4 centimeters. The diameter then would be 2 radiuses, or 8 centimeters. Okay, a long, long time ago, well before television, people began to wonder things about their world. You know, they'd look for relationships. In fact, I think the first known recording about this pi went back to 1650 BC. It was on a Egyptian papyrus, and that was the first one that I know of recording of pi. But anyway, these people were sitting there would measure things, and if you look, if I took this circle and I measured the distance around the outside, and this is the only thing I have here to actually measure the distance around the outside of this circle, I'll hold that there. I'm going to try and measure this as accurately as possible, but without taking a ton of time because I don't want to bore you guys watching me play with string. Okay, and I say right about there. There's a measurement, the circumference of the circle, the distance around the outside. Okay, and I took this and I actually measured it with a ruler. Here's my ruler. Lay the string down here. Line up on the edge. Where did I put my mark? Okay, I got this. Okay, and it looks like, I don't know if you can see this, my mark is right about here. It's in between the 1 and the 2, so I got 25.1, maybe 3? So I got 25.13 centimeters is my distance around the outside of the circle. And if I took this number and I divided by the diameter, so if I took 25.13 and I divided by the diameter, I would get, let's see what happens. Oops. 25.13, can you see that? 25.13 divided by 8, and I get, look at that, 3.14125. Equal to 3.14125. Actually, the more accurate I would measure, that's pretty accurate to get that anyway, but the more accurate that I would measure, the closer would actually get to this number pi. So they found that circumference is equal to pi times diameter. The way they found it, though, was when they took circumference and divided by diameter, it always equaled this number pi. If we were to solve for C, we would get C is equal to pi times the diameter. And there's our formula. When we come up with a formula for area, we're also going to have to use pi. And I just wanted to make sure that you understood what pi was and where it came from. Again, measuring the outside of a circle, dividing by its diameter, comes up with this number. Pretty cool, huh? Okay, now that we know that pi is 3.14 and where it came from, we want to find the area of this circle, and we want to do it knowing that the area of a parallelogram is base times height. We want to use this information to find the area of this circle. What we're going to do, first, I think we should measure the diameter of our circle. So let's do that, and I'm going to do this in centimeters. So we have some information about it first. Looks like this is 12 centimeters. So the diameter is equal to 12 centimeters. That means the radius would be half that, 6 centimeters. And what we want to do is we're going to take this circle and we're going to dissect it, just like we did the parallelogram. So I'm going to fold this in half and in half again. And then I'm going to cut this thing up and see if we can rearrange this into a parallelogram. If we can, we're in business. Ignore the writing here. You know where this thing came from. Okay, so I got this. I got this. Now, if I wanted to rearrange these pieces, and try and make a parallelogram out of it, it's not going to work like this. Okay? That doesn't look like anything like it. But if I took these pieces and keep cutting them up, what would happen? Let's see. This is going to take me a long time. What I'll do is I'll cut it like this now. Okay. Yeah, since these are all the same, I should be able to just take this, put it on top, and cut each one. Thank you for your patience. Now it's a lot easier to move this paper around when this isn't here, so what I'm going to do is move this out of the way. Alright, now if I took this, and you see I could put this together, and I'd still have my circle. Okay, if I put them all together, it's still going to be the same circle that I had before. It's just, and the area is still the same, it's just cut up into many pieces. But if I added the area of all these pieces together, it would be my same circle. It's kind of hard to mess with this. Alright, you get the idea. So, now what I'm going to do is I'm going to take these and I'm going to alternate them. I'm going to put them together like this. Taking a long time, sorry. There. It's a little crooked. But look at this. This is starting to resemble a parallelogram where this is parallel to this and this is parallel to this. In fact, the more you cut this up, the greater it resembles a parallelogram. If I took this whole thing and just kind of slid it down so I could bring my paper back. Okay. This distance, I wonder if I could put it on top. Let me see if I can get it on top. Nope. Okay. This distance on the outside, when I have my parallelogram, this is actually kind of bumpy here, right? This is bumpy, and this is bumpy down here, because this represents right here the outside of the circle. So this is 1/2 of the circumference. Here is the other half of the circumference. The height, the perpendicular distance here, is the radius, because this is half the circle. Okay? So this is the radius. Now, if I took this information, I said area then is equal to base times height of the parallelogram, where base is 1/2 of the circumference times the height, which is the radius. I know that circumference is equal to pi times diameter, or it's equal to 2 times pi times the radius, because 2 radiuses is the diameter. So I could take 1/2 of the circumference, and again the circumference is 2 pi r times r. 1/2 of this 2 pi r is is pi r times r. R times r is r squared. The area of a circle is pi r squared. And again, we took base times height of this parallelogram. Base is half of the circumference of the circle. So I took base as half the circumference of the circle times the height of this parallelogram, which is the radius of the circle. Then I said, all right, well, the circumference is 2 pi r. I used this one because I already had an r in there, and then I combined like terms. So I had 1/2 of 2 pi r. 1/2 of 2, this eliminates each other, leaving just the pi r. This should be scribbled out a little better. Then you have r times r, which is r squared. Pi r squared, area of a circle. Pretty cool.